Hi, this is your video for section 9.3 about estimating a population standard deviation. The objectives in this section are 1. Find critical values for the chi-square distribution, and 2. Construct and interpret confidence intervals for the population standard deviation. So objective 1 is to find critical values for the chi-square distribution. So first of all, let's talk about the point estimate for a population standard deviation, since that's what we're trying to estimate in this section. The sample standard deviation, S, is the best point estimate for the population standard deviation, sigma. The chi-square distribution is what we're going to use when we're estimating a population standard deviation. If a simple random sample of size n is obtained from a normally distributed population with mean mu and standard deviation sigma, then chi-squared equals n minus 1 times s squared divided by sigma squared. So in this situation, the chi-squared right here is our statistic that comes from our sample. And this has a chi-square distribution with n-1 degrees of freedom. Now the chi-square distribution looks different than the other distributions we've dealt with. For one thing, it's not symmetric. The normal distribution and the t-distribution both were symmetric on either side of the mean, but the chi-square distribution is not. In fact, it's skewed to the right. Now the shape of the distribution depends on the number of degrees of freedom, just like the t-distribution did. So here are some pictures of different chi-square distributions for different values of n. So the blue one right here is with only 2 degrees of freedom. The red one is with 5 degrees of freedom. The orange one is with 10. The green one is with 15. And the purple one is with 30. So you can see that as the degrees of freedom gets bigger, the chi-square distribution gets closer to being symmetric, and it also sort of moves over to the right. Another thing that's different about this distribution is that the values of chi-squared are non-negative. In other words, this graph starts at 0 and goes to the right. There is nothing on the left side of 0. This is going to make things a little bit different when we try to find critical values from this distribution. Because it's not symmetric, we have to find the two critical values separately. The value of alpha is still divided between the two tails, and we're going to use n-1 for our degrees of freedom. So what we'll do is we'll take our alpha, divide it equally between the two tails, so we have alpha over 2 in this tail and alpha over 2 in this tail. The chi-square distribution, we always go from the number to the right. So we'll find this value by looking at going from here to the right. We'll find this value by looking at going from here to the right. So here's an example of finding critical values. We want to find critical values for a 95% confidence level and a sample size of 19. And again, right now, since we're doing confidence intervals, we're actually looking at the middle 95% of the distribution. So we're taking the alpha, which would be 5%, and dividing it equally between the two tails. So alpha over 2 is 0.025, and our degrees of freedom is n-1, so in this situation it's 18. Now the way we're going to find the critical values for this distribution is just by using a table. There is a program that you can download to your calculator, but that's a little bit complicated, so it's easier just to use the table for this. And here's what the table looks like. This is just copied out of your textbook. We have 18 degrees of freedom, so we're going down to the 18 row. And then we have to look under both alpha over 2, which is 0.025, and 1 minus that, which is 0.975. So here's the value in the 0.975 column, which is 8.231. The value in the 0.025 column is 31.526. So those are our two critical values. Our second objective in this section is to construct and interpret a confidence interval for a population standard deviation. So the requirements for doing this are that the sample has to be a simple random sample, and second, the population must have normally distributed values, even if the sample is large. So no matter what the sample size, the original population has to have a normal distribution. Now, to construct this confidence interval, because our distribution isn't symmetric and our critical values are completely different, we just do the two limits separately. We don't actually talk about a margin of error in this case. So here's how we find those two limits. Notice our population standard deviation is in the middle of our interval. So our lower bound is the square root of n minus 1 times s squared over our critical value that was on the right. So this is our critical value for alpha over 2. Our upper bound is the same thing, only the critical value is the one that came from the left. So that's the 1 minus alpha over 2 critical value. One thing that's a little confusing here is that chi-squared automatically has this exponent of 2, but that doesn't mean that we're squaring anything. This whole symbol right here and the whole symbol right here are just the critical values that we find from that table. The only thing that we're squaring in this formula is the s, here and here. So here's an example. The proper operation of typical home appliances requires voltage levels that don't vary much. Listed below are 10 voltage levels recorded in a home on 10 different days. These 10 values have a standard deviation of s equals 0.15. So this is our sample standard deviation. We're going to use this to construct a 95% confidence interval estimate of the standard deviation of all voltage levels in this home. So here are our values, and the sample standard deviation has already been found for us. It's 0.15. So we have 10 values, so our n is 10, our s is 0.15, and our alpha is 0.05 because we wanted a 95% confidence level. So to find our critical values, we're going to look in the table using 9 degrees of freedom under alpha over 2 equals 0.025 and 1 minus alpha over 2, which equals 0.975. This gives us two critical values, 19.023 and 2.700. And when you're using this formula, remember that the bigger critical value goes on the left side, the smaller critical value goes in the formula on the right side. So here's our formula. We're taking the square root of n minus 1, which is 10 minus 1. Here's our sample standard deviation, 0.15, which is squared. And then on the bottom, we just have our critical value. The same thing on this side. So if we calculate these two, we get 0.10 on the left and 0.27 on the right. So those are our lower and upper bounds for our confidence interval. The interpretation for this would be that we are 95% confident that the true population standard deviation, sigma, is between 0.10 volts and 0.27 volts.